Alright, welcome to section 4.2. Today we're going to do operations on functions, and our objective will be to perform operations on functions and to determine the domains of the resulting functions. Alright, so it is possible to combine functions to create a new function. For instance, a very common combination of functions would be this expression: r of x minus c of x. Now, we use r of x quite often to represent a revenue or an income function right there. So revenue minus, and guess what? This c of x would be cost. And in the business world, what do you think revenue minus cost is? That's why it is profit, p of x. So there we go. So profit is the difference between the revenue and the cost function. All right, and so what have we done? We've done operations on functions to create a new function, in this case, a profit function. So the sum, difference, product, and quotient of functions. Each function listed below is defined, and remember this symbol, for all x in the domains of both f and g. So the sum of f and g. Now we have special notation for operations on functions. We just write that f plus g of x. Do you get that? We have the function f plus the function g in terms of x. And so what is that? That's nothing more than f of x plus g of x. Number two, the difference of f and g. So that's going to be an f minus g of x, and that's how you say that. But what is that? That is nothing more than f of x minus g of x. And then, of course, the product of f and g. Well, that's going to be f times g of x, or f of x times g of x. And then the quotient of f and g, which is nothing more than f over g of x, or f of x divided by g of x. And now note the comma right there. Well, what number can we not divide by? 0. So when I do the quotient of two functions, I have to be aware of domain restrictions. I know that g of x cannot equal 0 here. Okay. So I'm going to give you a linear function and a quadratic function, and we're going to find a rule for each function, and then also if there's domain restrictions, we had better talk about them. So let's start with f plus g of x. So again, all I'm doing is adding these two functions together, and I'm going to look at them and I'm going to put the sum of these two functions in descending order. So x plus 1 plus x squared minus 1. In descending order, I would start with my x squared. And then I have an x. And then I have a 1 and a negative 1. So if I add those, they would cancel. So f plus g of x is nothing more than x squared plus x. And that's a polynomial defined for all real numbers. So we don't have any domain restrictions. Okay, now f over g of x. Well, that's going to be f of x, which is x plus 1, over g of x, which is x squared minus 1. Okay, before I do this, I'm going to simplify g of x so I can hopefully do some canceling right here. So isn't x squared minus 1 the difference of squares? And wouldn't the two factors be x minus 1, x plus 1? Order doesn't matter there. And then if I put f of x over g of x, wouldn't my factors of x plus 1 simply cancel, leaving me 1 over x minus 1? And now you see the divisor, which cannot equal 0. But this leads to a very common mistake. Okay, there's going to be a domain restriction here, and it's obvious to me that x cannot equal 1. But when you talk about the domain of a quotient of functions, all right, you've got to think about what you originally had before you simplified. And that would have been x plus 1 over x plus 1, x minus 1. So x cannot equal negative 1 or positive 1. X cannot equal, don't forget about both of those factors that were originally in our divisor for g of x, plus or minus 1. Okay, so let's talk about adding and subtracting functions in the plane and what the graphs are going to look like. Now, this may seem just a little bit more abstract, but it's really quite simple. So let's start with a very rough sketch of f of x equals x minus 3 halves quantity squared plus 2. Now I hope you see a parabola in completed square or vertex form right here. So what's that going to look like? Y equals f of x. What's that going to look like? Well, remember your completed square form of a parabola? Y equals a times the quantity x minus h squared plus k. Now, this gives me the vertex of my parabola rather than immediately the y-intercept. And that vertex will be hk. So, if I look here, okay, what would the coordinates of that point have to be? Well, x minus h is x minus 3 halves, so this x coordinate of the vertex will have to be 3 halves, and then my k is 2, the y coordinate is 2. Now that is going to be the vertex of my parabola, so then I'm going to draw a rough parabola with the vertex right there. Okay, and I'm not worried about scale or anything right now. Okay, now let's graph g of x, which is linear. Okay, and I have a y-intercept of 1, so I'm going to try to put this to scale here. So if this is y equals 2, then y equals 1 would be about halfway, right in there. Okay, and then I have a slope of negative 1/2. Well, that means I'm dropping 1, and I'm running 2. Well, there I'm at 1. There I'm at 1.5, so 2 would be right out in here somewhere. Okay, so that is the point 2, 0 right there. And 2 points to terminal lines, so here is my line right there. Okay, now here's the concept of using two given graphs to come up with the graph of the sum of those two given graphs. Okay, it's very simple. I'm adding this linear function g to the quadratic function f. Now, let's keep it very simple. The vertical arrows from the x-axis to the graph of g, which would look like that, the blue ones are positive, the red ones negative values, are simply added to the graph of f. So I would start right here where g is 0, and I would put a point on f plus g right there. I missed it a little bit there. And then the blue arrows will be over here on the left, and the red arrows will be over here on the right. Now look at this. So a very rough sketch of f plus g of x would be this graph right here. Isn't that cool? And there it is. Wow. Okay, now we have two functions f and g, and we're going to take a look at those two graphs, and I'll bet you this time we're going to subtract them. Let's find out what happens here. So let's start with a graph of f. Okay, well, f has a y-intercept of 2.1/2, so I have to put that up here somewhere. Oh, and I went right to the line. So there's my y-intercept of 2.1/2, and right here I have a slope. I'm dropping 1, and I'm running 2. And I don't have anything scaled, so I just drew it pretty rough just like that. Now, let's go the quadratic, which again is in completed square form, so I can see my vertex would be 3/2, 9/4. So let's try to put that in perspective with this linear graph right here. So this vertex. Well, the vertex right there, I didn't label it, and I'm sorry, but that's 3/2, 9/4 right there. All right, but the concept I really want to get to here is, now how can I visualize the difference between those two functions? Well, when we added the two functions, oops, I went too far there. Let me get back real quick. We talked about the vertical arrows from the x-axis to the graph of g, and we just added those values to the graph of f to get f plus g. Now here, we're doing the difference. So instead of going vertical arrows from the x-axis, we do the vertical arrows between the two graphs. So f minus g would look like this. The vertical arrows from g of x to f of x, because this is the difference of f and g. And these would be positive values, and these would be negative values. And there, that's 0. There's nothing there, no magnitude there. Now these arrows are put on the x-axis. So the vertical arrows from g of x to f of x give the output of f minus g. So check that out. I just translate those down to the x-axis, and the rough sketch of this curve, f minus g of x, would look just like this. There it is. Kind of rough there, but not bad. And that's what's happening here. All right, so let's talk about the concept of composite functions now. The composite of functions. The composite of f and g denoted f composed with g, that's what that open dot means right there, composed with, is defined by two conditions. Number one, f composed with g of x, which we can also write as f of g of x, which is read just what I said, f of g of x. Okay, and number two, x has to be in the domain of g, because again, my input is x, and x has to be in the domain of g to get an output g of x, and then that g of x has to be in the domain of f. Okay, and how do we read this? F of g of x. Oh, or over here I would say f composed with g of x. Now, let's draw a picture of this. So f of g of x, I like to diagram this actually going from right to left. So I'm going to start with an element x. And then what am I going to do? G of x. So let's apply the function g to that, giving me that g of x. And then what am I going to do to my g of x? I'm going to apply the function f to that to get what? That's right, f of g of x. So f of g of x is equivalent to f composed with g, just like that. That's a great diagram. Okay, now we can use our graphing calculator to graph a composite function. It may help us see that its domain needs to be restricted. So when we do composites, many times we're going to have restricted domains, and there's something you have to be very careful about, which you'll see in just a moment. Okay, so let's take the f of x as the quartic binomial, x to the fourth minus 3x squared, and g of x is the root function, radical x minus 2. So we're going to find f composed with g of x, or f of g of x if you prefer, and give the domain of the composite function. So first, you have to be an expert at finding composites. So when I'm finding a composite, not like the diagram where I kind of work right to left, I'm going to work left to right. So I'm going to start with the function f, which is x to the fourth minus 3x squared. But I want you to notice something. Instead of inputs x, I just put a good parenthesis wherever I see an x. So this is x to the fourth minus 3x squared. But now we're talking f of g of x. So instead of the input x, I have the input g of x, which is root x minus 2. So in each of these parentheses, I'm just going to put a radical x minus 2. Now I'm going to simplify this. Now the first term, by laws of exponents, the square root of x minus 2 is actually x minus 2 to the 1/2 power. And I hope you know that x minus 2 to the 1/2 to the fourth, that would be a power of a power, and that would give me an x minus 2 quantity squared. Now, minus 3, and then I have radical x minus 2 squared. Well, if I square a square root, I just drop the root. But if I use my laws of exponents and think of it that way too, that's x minus 2 to the 1/2 squared, and a power of a power, that would be x minus 2 to the first. So that's negative 3x minus 2. Now, let's expand and then combine like terms. So x minus 2 quantity squared would be an x times x squared, and then outside and inside would be a negative 2x and another negative 2x for a negative 4x. And then negative 2 times negative 2 is positive 4. And then distribute this negative 3 to get a negative 3x. And then negative 3 times negative 2 is positive 6. And combine like terms, and we have our simplified composite. So I see 1x squared minus 7x's plus 10. Okay, there it is. But now we have to be aware, is there a domain restriction? And if I look at my simplified expression for the composite f composed with g of x, I see a parabola which would be defined for all real numbers. So I'm thinking I'm good to go. You must remember, all right, you have to look at the unsimplified version of your composite to determine if you're going to have some domain restrictions. So I can't look at the graph of x squared minus 7x plus 10, which is a parabola that would go on forever in both directions. I have to look at this function before I had simplified it. All right, and I see some radicals, so I know there's going to be domain restrictions here. Now, if I'm going to use technology, I just graph this function exactly the way I see it. So I'm going to put y equals exactly this, and then probably just graph it on a simple window here. So here's my final answer. F composed with g of x in simplified form would be x squared minus 7x plus 10. And then I put my unsimplified version into my calculator as y sub 1, and look at this graph. I think you can clearly see that the x values in this composite would be, well, that's an x equals 2 right there. So it looks to me like the domain is going to be, and look, I just, put this graph onto the x-axis, so I see x is greater than or equal to that 2 right there. And there it is. So a graphing calculator might help you see the domain restrictions of any composite, but make sure you don't put the simplified version into your calculator. Make sure you put the version of the composite into the calculator before you simplify it. Okay, let's go ahead and confirm the previous domain analytically, because what if our calculator's not handy? All right. Well, personally, I think this is easier than using the technology. You just need to understand the concept that, okay, what? F composed with g of x. Okay, the domain of f composed with g of x. Well, that means any x has to be in the domain of g, and then any output g of x has to be in the domain of f. So I'm going to start and I think about the domain of g right here. Well, do you guys see the radical right there? All right. You know that this expression x minus 2 would have to be greater than or equal to 0, or we would get an imaginary number. So x minus 2 has to be greater than or equal to 0. There's my first restriction right there, and I hope that looks familiar. Now, f is a quartic polynomial. So x minus 2 has to be greater than or equal to 0, but then I can put any g of x into f of x because f of x is a polynomial, and polynomials are defined for all real numbers. So the domain for this composite would be x minus 2 is greater than or equal to 0. And there you have it. So my final answer here analytically would be f composed with g of x is x squared minus 7x plus 10. Remember our simplified form of this composite, and x has to be greater than or equal to 2. Okay. All right, let's do this one more time. So given f of x equals 1 over x and g of x equals x plus 1, let's find f composed with g of x and g composed with f of x, and give the domain of each composite function. All right, so let's start with f composed with g of x. All right, and if you want to write that f of g of x, you can to make it easier. All right, but I'm just gonna, again, I'm gonna work from the left to the right. So I'm starting with my function f right here, which is 1 over x. But this is f of x, and this is f of g of x. So in f of g of x, I'm going to replace the x in f of x with g of x, which is what? X plus 1. And then this is rational. I have a divisor, and my divisor cannot equal 0, so that implies x cannot equal -1. All right, now let's do g of f of x. I'm curious. What's this going to look like? So now we start with the function g of x, which is x plus 1. But let's leave the x blank, plus 1. Because this is g of x, which is x plus 1, but I need g of f of x. So I have to replace the x with f of x, or 1 over x. Now, there it is, and that's simplified. So now, what's my domain? Well, I have this term that is rational. My divisor cannot equal 0, so I know x cannot equal 0 here. So we did this to make a very important point. Compositions are not commutative, all right? F of g of x might equal g of f of x, but not very likely. It does happen once in a while. And with that, I'd like you guys to do the homework for 4.2, which is 3, 17 through 25 odd, 33, 35, and 37. Do these problems carefully. Become an expert at finding a simplified composite function and determining its domain. Thank you. You guys have a great day.